Hello, everyone. I will launch the presentation. Hello, everyone. Today we will continue the course which was organized by the Department of Postgraduate Studies from the Institute of Cybernetics of the by the Viktor Glushkov Institute of Cybernetics of the National Academy of Sciences of Ukraine. They remind you that the course developer is Butenko Sergey, professor of Texas A&M University. The course advisor is Piotr Ivanovich, Doctor of Sciences from the Institute of Cybernetics, and the course instructor is I, Valaviki Lena Ivan. So again, as we said, we are continuing the set of lectures, the sequence of lectures referring to the survey of optimization. Today we are in lecture 6, and which will mostly relates to the simplex method, actually the first part of it. So specifically we will cover the following topics today. Again, we will go over the major methods of solving LSP as we did last time. Then we will introduce the characteristics of LPs in the standard form. Also, we will introduce how to convert an LP to standard form, or including converting constraints to equalities. Then we will formulate and actually introduce a dictionary format of LP standard form. And as the preparatory part for the simplex method, then actually we will go over the algorithm of the simplex method and demonstrate how we can solve the problem introduced actually a long time, and which we solve every class, heavenly Pouch incorporated, using the simplex method. Now, again, let's review that the major methods of solving LPs are the graphical method if we have a two-variable case, and this is the method which we went over in the previous lecture. So those who didn't attend it, please go over the video and the presentation posted on the site. Also, another method is the substitution method, the linear combination method, the simplex method, which we will introduce and apply today. Hachiyan's algorithm, the ellipsoid method, methods which are referred to as unknown shores methods, and Karmakar algorithm, which is based on the integral point method. Now, a little bit about the historical background as related to the simplest method. Recall that George Danzig is accredited as the founder and the developer of this method. He actually worked on planning methods for the US Army Air Force during World War II, using a desk calculator, as the history says. During 1946, his colleague challenged him to mechanize the planning process to distract him from taking another job. And Danzig formulated the problem as linear inequalities, being inspired by the work of Vasily Leontiev, who at that time actually was working for the US government too. However, at that time, in 1946, he didn't include an objective as part of his formulation. Without an objective, a vast number of solutions can be feasible, and therefore to find the best feasible solution was quite complicated. For that, he used military specified ground rules that describe how goals can be achieved as opposed to specifying actually a goal itself. So Danzig's core insight was to realize that most ground rules can be translated into a linear objective function, and which needed to be maximized. So development of the simplex method took about a year, and it happened over a period about from 1946, 1947, no, approximately a year. Now, after that, Danzig included an objective part as part of his formulation, and the problem became more mathematically tractable. The name simplex was suggested and actually derived from the concept of simplex by an Israeli and American mathematician whose name was Motzkin. So this is actually a historical background for the simplex method, and now we will go over some preparatory steps which are necessary for us to implement and to apply actually this method. So in this lecture, we will start discussing one of the most common solution method for linear programming, which is called the simplex method, as I stated before. But first, in order to start, we need to slightly modify the description of the problem that we are working with by putting it in standard form. The simplex method works only with LPs in the standard form, allowing only equality constraints along with non-negativity of all the variables. Why? Because equalities are much easier to deal with than with inequalities. So by putting LP in the standard form, we will reduce it to a problem where we only have the equality constraints or equations and the non-negativity constraints. So therefore, the rules, the prompts which we will need to follow is that all variables involved are restricted to be non-negative, and all constraints are equality with constant non-negative right-hand side. Now, how do we actually, in order to convert an LP to a standard form, we need to go over some rules. It may require new variables and rearranging the initial constraints. So an equality can be multiplied by -1 to get non-negative right-hand sides. Then inequalities can be converted to equalities by adding or subtracting non-negative slack variables, and unrestricted variables can be dealt with by writing the variable at the difference of two non-negative variables. Now let's consider the following example and how we practically convert an LP to a standard form. So this is an LP in the form which we are accustomed to, with two decision variables x and y, with the positive coefficients at which accompanying actually each of them. Also, we have two inequality constraints and non-negativity constraint actually for the decision variables. Let's start converting. So what we do first, we introduce two new variables, which we call slack variables, denoted by S sub 1 and S sub 2, such that, first of all, they are non-negative, as you can see here. Then, S sub 1 measures how much over 1 the quantity x plus 1 is. Recall that 1 appears on the right-hand side in the first constraint. And S sub 2 measures how much under 0 the quantity -0.05 plus 0.07y is. Recall that 0 is the right-hand side of the second constraint. At step 2, we update the model accordingly, and now we see that the objective function stays the same. The subtracted slack variable denoted as sub 1 is added to the first inequality, and the inequality relationship is changed to equality, and the slack variable s sub 2 is added to the second constraint, and the inequality is turned into the equation, though the last constraint, the only inequality which is represented here, is the non-negativity constraint. And we see that instead of 2 variables, now we have 4 variables. So the newly introduced variables are included into the non-negativity constraint. It is important to mention that the quadruple x, y, s sub 1, s sub 2 is feasible for the updated model. If it is feasible, then the pair x, y is feasible for the original model. If the pair x, y is feasible for the original, then the quadruple, and you see that here the newly introduced variables are replaced by the differences between the right-hand side and the left-hand side. and they're substituted by the expressions. So therefore, this extended quadruple is feasible for the updated problem. So since the objective only involves the decision variables of x and y, the two problems have the same solution. So if the ice constraint, and here actually we distinguish two cases. When the relationship is greater than or equal type and less than or equal type. So if a constraint is of greater than or equal type, we introduce a negative, a non-negative excess variable denoted as E sub j and subtract it from the left-hand side of the constraint to obtain an equality. Here we are, so this is the greater than or equal relationship. So therefore, we subtract, here subtract, and here it is, the excess variable E sub j. So where the excess variable can be introduced as the difference between the right-hand side and the left part of the equation. Recall that it was negative. It has a negative coefficient, so that's why for us to make it possible, we divided the both sides by negative 1. So that's why we have negative 4 here, and we assume what is non-negative. Actually, the non-negative constraint is indicated by this relationship. It is greater than or equal to 0. Then, if a constraint is of type less than or equal, so we actually flip the inequality relationship, we add a non-negative slack variable s sub I in the left-hand side of the constraint to turn it into an equality. And here we have, so this is less than or equal type. So here we add the slack variable. Again, the slack variable can be expressed as the difference between the right-hand side and the left-hand side, the remaining actually expression. And again, and it is non-negative, so we actually include the non-negativity constraint here. Well, let's consider more examples. Let's consider a complete LP model and convert it into a standard form. So no, the original one is actually a maximization problem. The objective function is introduced by 3 variables, x sub 1, x sub 2, x sub 3 decision variables, and the constraints subject to are expressed by one inequality greater than or equal, then another is less than or equal inequality. The third constraint is already an equation, and the last constraint actually refers to the non-negativity of the decision variables. How we convert it, as we said here, as it is greater than or equal type, so we introduce a non-negative excess variable E sub I and subtract it from the left-hand side for us to get the equality relationship here. Then here is the flipped actually relationship, so it is less than or equal. Here we add the slack variable, let's denote it as S sub 2, for us to achieve the equation in this part. As here it is an equality already, so we leave it unchanged. And into the last constraint, it is the only inequality in this model, we add 2 more variables, E sub I and S sub 2. We can write a standard form LP in an equivalent dictionary format where the slack and excess variables are expressed through the remaining variables. Now, as here we have another LP model, as you see here, we mostly have less than or equal, so they're quite standardized. So therefore, actually, we convert it into the dictionary form, which, in some part actually resembles a system, of equations, linear equations. So here, the objective function, first of all, receives a name, Z. That is important, and it appears above this line. So there is a line which separates the objective function from the constraints part. Here, S sub 1, S sub 2, S sub 3, S sub 4 are slack variables. No, we do not explicitly state this, but we keep in mind that all variables are non-negative in the dictionary format. The variables x sub 1, x sub 2, x sub 3 were initially non-negative, and the way we introduce the slack variables, so they are non-negative too, according to the definition. So now we have 7 variables, 3 original ones, and 4 slack variables, 7 altogether. So we call this representation additional form of the LP. And in it, we have the abjection function in the row 0. Sometimes we call it 0. And the rows 1, 2, 3, 4 correspond to the modified constraints. No, modified, I mean from inequalities, modified from inequalities. So with the dictionary representation, we reduce the problem of solving the original LP to the solving of this linear system. This linear system is subject to non-negativity constraints for all the variables, both these ones and these ones. And we do not need to just to find just any solution to this system. Rather, we need to find the solution such that Z here is as large as possible, because we deal with the maximization, actual optimization model. So we want to maximize this objective here. As soon as we have the solution for this representation of our algorithm, we do not really care which of the variables are the slack variables and which of them are original. So what we will do next, we just rename the slack variables to x's by starting with the index 4, as indices 1, 2, 3, 4 have been already reserved for the original variables. And we get the following. So first, we rename the slack variables. X sub 4 now becomes as the slack variable 1. Then x sub 5 is slack variable 2. X sub 6 is slack variable 3. And x sub 7 is slack variable 4. We renamed the variables by using the same axis to show that we treat all the variables equally. Now the system has only x variables, which is convenient for us, and we need to find the solution to this system such that the objective is reached. So in this representation, we will call the variables kept in the left-hand side, the basic variable. Here you see they coincide. And the indices, the set of indices which corresponds to this set are 4, 5, 6, and 7. All the remaining variables, which were original ones, we call non-basic variables, denoted by x sub 1, x sub 2, x sub 3, so they were original ones. And the indices which correspond to this set of the variables are 1, 2, and 3. So obviously the number of basic variables, this one, is the same as the number of constraints in our LP. And the number of non-basic variables equals to the number of variables in the original LP and the number of variables in the Z, now it's actually Z, function in our objective. So typically the way we proceed with solving optimization problems, we start with some initial feasible solution, and then we try to gradually improve this solution step by step by building a sequence of solutions such that each next solution is hopefully better or at least no worse than the previous one. And we want this sequence to eventually converge it to optimal solution. So if we look at this dictionary here, how can we get an initial feasible solution from? One easy way to go in this case is by observing all the numbers in the first column here, referring to the free coefficients. So they are all positive, which is good. And we see that if we set x sub 1, x sub 2, x sub 3 to 0, we get rid of this part of the system. So we will have only 3 coefficients here. So then the part with variables here will disappear, and the value of x sub 4 becomes 3, x sub 5 becomes 2, x sub 6 becomes 4, and x sub 7 becomes 2. And this will give us a feasible solution to our problem because everything is non-negative as required. So everything is non-negative. Of course, this is definitely not the best solution, but at least it is a solution, because if we plug in the 0 values into the objective function, we receive that z is equal to 0, and it is not necessarily a great solution for maximization objective, but it is a feasible solution. So we need, and we needed to start the process. So, and no, what are the advantages? If we just set the variables into zeros, so then it is a very easy and straightforward way to get a feasible solution. This is actually a great advantage, even though it is definitely not the best one. Of course, we have to know that if some of these right-hand sides were negative, then we would not really get a feasible solution by setting all of these to 0 if they were all negative. However, by now we may assume that we have all positive right-hand sides for these ones, and we'll worry about no, if they are negative actually later. So this is called the initial feasible dictionary. Here, this one. Okay? No, and on the previous one. The variable that we have here on the left-hand side of this one. Remember that we started with using the slack variables. Are the only variables that can be positive in this representation so far, as soon as the others are set to 0. We call these variables the basic variables, because we assume that they form a base. And all the remaining variables, we will call them non-basic variables. So the one that we set to 0, here they are, will represent their non-basic variables again. So by setting our non-basic variables to 0, we come up with their basic feasible solutions which correspond to this feasible dictionary. Now look here. If all variables have non-negative values in the basic solution, then the solution is called a basic feasible solution denoted by BFS, and the corresponding dictionary is called feasible. So therefore, this is a feasible dictionary. So the initial BFSs are the original variables are set to 0, and the newly introduced variables, like variables, are equal to the right-hand sides of the equality. So therefore, x sub 4 is 3, x sub 5 is 2, x sub 6 is 4, x sub 7 is 2, and we can find the value of the objective function, which is 0. Again, we said it is not the best solution, but it is a solution. So the way our method will proceed, we will try to build a sequence of these BFSs, basic feasible solutions, such that each next basic feasible solution is better or at least no worse than the previous one. And at the end, we want to obtain a basic feasible solution for which we can guarantee that it is optimal. Yeah, so it maximizes the objective function as much as it is possible. So at step 0, we have this dictionary. So this again, call it is the initialization actual step. Our initial basic feasible solution is given by the one presented on the slide. Here it is. The question is, how can we obtain a better solution from the given solution? So let's look at the objective, at the zero row. Zero. Yeah? No, let's think how we can improve our objective. No, definitely, we can improve our objective by increasing each individual variable here. But as right now all the variables at the zero level, so let's start with some of them. So for example, let's look at the coefficients at these variables and select x of 1. So what happens if, say, x of 1 is equal to 1? We set it equal to 1. So it was 0, now it is 1. Then the z value becomes 5. Before that, it was 0. So it is definitely non-negative, and definitely it is greater than this one. So therefore, there is an increase, which is good. So we are moving towards maximization. So it is greater. So now, what will happen to these variables? If we set x of 1 from 0 to 1, then x sub 4, row 1, becomes 3 minus 1, it is 0. It is 2, I'm sorry. 3 minus 1 is 2. Now here we add, so therefore no matter which value we add, it will be still positive. Moreover, it will be maximized without any restriction from the upper restriction. So therefore it is unbounded from this perspective. No, generally we can ignore all 2. It just really doesn't matter. Though 2 plus 1 is 3, no, which is still positive. Now, x sub 6, 4 minus 2 times 1, it is 2, it is non-negative, so it is good. And here 2 minus 2 times 1 is 0. Still non-negative, yeah, so they are all still non-negative, therefore this solution appears to be feasible. So we can make this increase meaning actually increase x of 1 by 1. Let's see if we can increase the objective value by increasing the value of x sub 2 instead of x sub 1. So now let's again, the other variables are 0, and this one we set to 1. So what happens? No, again, the objective function becomes 5, which is good. It is better than 0. It is greater than 0 if we speak about maximization. So therefore, definitely it is. This is the good news. Now let's go over the constraints. What happens here? 3 minus 3 times 1 is 0. Good, still non-negative. Then x sub 5 is 2 minus nothing, so therefore it is 2. Good. X sub 6 is 4 plus 1, which is 5. Good. 2 minus 3 times 1 is negative 1. Here we can see that the increase of x sub 2 by 1 unit would be infeasible because we get a negative solution, but we defined our variables as non-negative, meaning that actually we cannot do it because we get into the infeasible region. Now, what we have seen from this exercise is that we can increase the objective value by trying to increase the values of some of the variables that are included into the objective function. And the objective depends only on non-basic variables. Here they are. By looking at the non-basic variables with positive coefficients in the objective, we can actually increase the objective. Why? Because if the coefficients were negative, by increasing the variable which has a negative coefficient, we actually decrease it. Where we are. here. We actually decrease it. So that's why we do not consider actual negative coefficient. Whenever we have a positive coefficient in the objective, it means that there is a potential to increase, and we should try to use this to improve our objective function value. So we showed it by looking at the first two variables, but the same is true about the third variable. I just don't want to go over it because it will be actually the same. But the amount by which we can increase the variable is limited. We cannot increase as much as we want. Whenever I have some minus in the constraint, the amount I can increase, say x of 1 is bounded by this value. So here it is bounded by -3, here is bounded by -3, 2, well, no, and the like. But now to determine to which value we can increase x of 1 while staying within the feasible solutions, let's look at the constraint equation. For row 1, I cannot increase x of 1 by more than 3. So, and 3 is determined as the ratio of 3 and absolute value of -1, which is actually 1. So 3 divided by 1. Here it is positive, so we ignore it. Then in row 3, we cannot increase x of 1 by more than 2. Because, so this is actually the 0 value which will appear. So therefore, the limit of increasing the x of 1 will be 4 divided by absolute value of 2. And here it will be, no, so here we cannot actually increase x of 1 by more than 1, just because 2 divided by 2 is 1. Yeah? So therefore, so what we did, so the maximum how we increase x of 1 is the minimum of such ratios. So what we did here to determine the highest possible increase of 4x of 1 was what we call the minimum ratio test. And this test is very important to do iterative, as the basis for performing iterative improvement. So based on the pivot variables and columns. So the rule is, in order to increase the value of the objective function z in the feasible dictionary, increase the value of 1 over the non-basic variables with the maximum positive coefficient in the objective. Then take a variable with the largest coefficient in 0 row, which is called the pivot variable, and the corresponding column in the table is called the pivot column. So now let's actually perform this ratio test in a more comprehensive way, more specifically, though actually we have done. So increase the value x of 1 is the largest possible coefficient in the objective of 5. Remember that 5 is the highest positive coefficient, though it refers to 1. Well, it refers to two variables, x of 1 and x of 2. So all the other remaining non-basic variables remain equal to 0. Now, here we have, as those are here, we actually, the constraint part is converted to this set of equations. And remember that there was a non-negativity constraint, so therefore all of them need to be greater than equal. So in order to satisfy the inequalities, x of 1 needs to be no greater than 1, meaning that the largest improvement for x of 1 is 1. So the largest is from here, the largest feasible increase for x of 1 is 1. Again, how we perform the ratio test is that we simply focus on the constraints where x of 1 has negative coefficients here in the dictionary. Here they are. Right? 1, 2, 3. Okay, what we did next, we just looked at the ratios of the constants to the coefficients absolute values. Well, and selecting the smallest ratio. So we call the smallest ratio the winner of the ratio test. And here is the rule. The largest possible increase corresponds to the smallest ratio of the free coefficient to the absolute value of the coefficient for x of 1 in the same row, assuming that the coefficient for x of 1 is negative. We say that the row in which the smallest ratio is achieved wins the ratio test. This row is called the pivot row. Note that the minimum ratio gives the value of x of 1 as it enters the basis. Before it wasn't there, it was non-basic actual variable. Now here we go. Here we go. So we select the highest positive coefficient at x of 1 in the objective. So therefore, the column which corresponds to this variable is referred to as pivot column. Then based on the ratios, okay, the smallest ratio, remember, corresponded to this value, to this actual line, to this row. This row is called the pivot row because x of 1 wins with this wins the ratio test. Then we express x of 1 through the other terms and the other variables and come up with such expression for x of 1. X of 1 is 1 minus 3 halves times x sub 2 plus a half of x sub 3 minus a half of x sub 7. And we substitute this value in the remaining rows of the dictionary. No, this is actually the final result of this substitution. So we substituted, then found the like terms, no, and so on and so forth, and perform some basically arithmetic and algebraic actual operations. The process of swapping the entering and leaving variables we are about to describe is called pivoting. Now, the variable which enters the basic is x sub 1. Here it is. It wasn't there. It was here. Now it is in the basic variables. And the variable which leaves the basic variables, well, this is x sub 7, is called the leaving variable. The entered variable is the same as the pivoting variable. It's just another name for it. So we updated the constraints accordingly by performing simple algebraic and arithmetic operations. Okay, and we have, so this describes essentially the step of the algorithm. And at every step, what we will do further, we determine the entering variables that will enter the basis, and this will be variable that has the potential to increase our objective, which means that it needs to go with a maximum positive coefficient in the objective function. So then, as a result of increasing the value of the entering variable, the winner of the ratio test will turn into 0 and will call the variable the leaving variable, leave the basic and become non-basic, as it was with x sub 7. Now we need to update our dictionary and make sure that we still have the same rule where all the basic variables are kept at the 0 value and are kept on the left-hand side and are set to 0. Non-basic are set to 0, and this one are basic, so the left-hand side. So broadly speaking, and okay, and then actually we can perform the iteration, repeating actually the same algorithm. Again, we see that there are two positive coefficients in the objective function. One is 5, The other one is 11 over 2 corresponding to the variable x sub 3. So therefore, there is still potential for improvement by increasing the value of x sub 3. Now, broadly speaking, we don't have to use the variable with the highest coefficient in 0. Any variable with a positive coefficient will do. Nevertheless, picking the highest possible coefficient is just a popular choice, and what this choice is referred to as the Danzig rule, because definitely we want to increase as much as possible, and not just logical, it makes sense for that to use the largest coefficient. So that is actually pretty much the same. So then we again repeat the steps which have been performed so far. We have an update in the list of the basic variables, so which correspond to the left-hand side, as we can set. Then again, non-basic are set to 0. In this case, we have x sub 7, 2. So the solutions for the basic variables will be 1, 2, 3, 2, and the objective function turns to be 5, which is better than 0. So therefore, there is an improvement towards maximization. Now, next step, we again perform pivoting as we did before. We have determined actually the coefficients, so we have determined the pivot variable, the entering variable. Now we need to determine the pivot row, again by finding the ratios. Okay, 2 divided by 3 halves will be 4 over 3. 3 divided by 5 halves will be 6 over 5. And 2 divided by 3 halves will be 2/3. Recall that again we refer to the constraints where the coefficients are negative at x sub 3. So this one is the minimum, so that is the smallest ratio. So therefore, according to the smallest ratio test, the last row, which corresponds to x sub 6, wins the test, wins the test. So therefore, then in this row, we express x sub 3 through the other parts, the other actual variables. Here we are, and we substitute it into the dictionary for performing the pivot. So, and what we get, so we substitute it first into the objective function, and again perform the like terms and simplify the expression. Then again, here the largest positive coefficient is 29 over 6. Then we go over, so here is the pivot column, so we will go over the coefficient x sub 2 in the constraints, and we have the ratios here. So here it will be 4 over 3 divided by 6 over, divided by 5 over 6, 1 divided by 7 over 2, 4/3 divided by 29 over 6, and the BFSs at this point are x sub 2, x sub 6, x sub 7 is 0. X sub 1 is 4/3, x sub 3 is 2/3, x sub 4 is 1, x sub 5 is 4/3, and the z value becomes 26 over 3, which is greater than 5. So therefore, we are actually moving towards maximization. Now, actually, let's decide which row wins. Row 4 wins because we select the minimum. The minimum of the ratios is 8 over 29, yes. So this row wins them. So we express x sub 2 through the other terms, obtain actually the expression for x sub 2, and substitute it into the dictionary. So, and we have for the objective function 10 minus 2x sub 2 minus x sub 6 minus x sub 5. What is interesting here? We have received that all the coefficients are negative, meaning that at this step, we can stop. There is no potential to increase the objective function. no matter how we increase all the variables, they will move lower. So they will make the function lower. So therefore, we may stop it here. And here we come up with the basic variables of x sub 1, x sub 2, x sub 3, x sub 4, and non-basic variables of x sub 5, x sub x sub 5, x sub 6, and x sub 7 here. X sub 5, x sub 6, x sub 7. So again, we set them to 0. By setting them to 0, we receive the value of 0 here. And we may conclude that this solution is optimal. So we cannot actually perform further optimization. Now, let's consider this method for solving the problem which we have been solving since the beginning of our course. That is Heavenly Pouch Incorporated problem. I didn't even put the text of the problem. Rather, actually, I just presented the formulation of the model, the formulated model, and I will quickly go over it. So this is a maximization problem. There are two variables involved. We stand for the types of products produced. For every unit of production of products x sub 1, the contribution is $15, and for every unit of x sub 2 product produced is the contribution is 25, and our goal is to maximize the profit. So also we have 4 constraints for this model and 1 non-negativity constraint for the decision variable. No, okay, let's go ahead. Step 1. We need to convert the given LP to a standard form by introducing slack variables as sub I, where they vary from 1 to 4, because recall the number of slack variables corresponds to the number of constraints, excluding the non-negativity constraint. So therefore, we have 4 SIs. No, and here they are, S sub 1. And now all inequalities are turned into the equations, but now we have 6 variables, because S sub 1, S sub 2, S sub 3, S sub 4 actually fall under the non-negativity constraint, so they can't be negative. So this is actually step 1. Step 2, we rewrite this model in the dictionary format by adjusting the columns corresponding to the variables and actually the column of free coefficients. The slack variables are expressed as the difference between the right-hand side and the left-hand side. These parts, this left-hand side, built at basic variables, and they are S sub 1, S sub 2, S sub 3, S sub 4. The other variables, x sub 1, x sub 2, built actual non-basic variables. Before we discussed the idea of the simplex method using the dictionary format, which helps to clarify or clearly explain the motivation behind each action taken by the method. So when the meaning of each operation is clear, spelling out all the variables at each step is unnecessary and time-consuming. Instead, we may perform the computations in the Tableau format here. So as a table, which facilitates quicker execution of pivots by performing elementary row operations. And we will illustrate this idea using actually this problem. This LP, LP corresponded to this problem. So first of all, in the first row, we have the labels for the Z, which is the objective, x sub 1, x sub 2 original variables, slack variables, s sub 1, s sub 2, s sub 3, f sub 4, right hand side, RHS stands for right hand side, and the basic. Interesting here. What is interesting here is that z is always basic, and it is treated as a variable here. So since the dictionary format is helpful for visual explanation of the ideas behind the method, and the tableau format is more handy for performing the computations, we will use both representations as we describe the steps of the Simplex method further. In both dictionary and tableau formats, we number the rows starting with 0. This is 0. And the other actually ones corresponding to the constraint. What is important here? In the table, we put the expression for the z as the difference between the left-hand side and the right-hand side. So that's why the coefficients appear as negative. So that actually worth mentioning. So the basic visible fault solution at step 0 is given in this table. So basic variables are s sub 1, s sub 2, s sub 3, s sub 4. Remember that they appear on the left-hand side. Non-basic variables are x sub 1, x sub 2. BFS, basic feasible solutions, we start with setting the variables to 0. Then we find the values for basic variables, which are s sub 1 250, s sub 2 300, s sub 3 is 2000, and s sub 4 is 350. And the value of the objective function is 0. So we are ready to perform the first iteration of the Simplex method. So let's analyze our problem written in the dictionary form. So at step 1, let's analyze it further. Okay. Remember that according to the algorithm, we need to select the highest positive coefficient from the objective function. That is 25. Then x sub 2 will represent the entering or pivot variable. So this column corresponds to the pivot column. And now we need to determine the row, pivot row. The pivot row is found as the ratio between the free coefficient and the coefficient at the pivot variable with a negative sign. So here we have 150 divided by 1, absolute value of it. 1, 300 divided by 1, and 2000 divided by 4. Here we are, and we need to select the minimum of them. Know clearly that the minimum of the three values is 300. So therefore, this line represents the pivot row. In the pivot row, we express x sub 2 through the other actual variables and parts of this, which is stated here, and substituted into the dictionary form, current dictionary form. So here we substitute, we perform the like terms, and find the updated value for the objective function as 7,500 plus 15 times x sub 1 minus 25 times s sub 2. So this is actually the updated objective function at step 1 iteration. So then we change these constraints actually accordingly. And updated one. And updated I will look further. So far, let's look at the tableau form. The tableau form, it will go like as we have the difference. So therefore, in the tableau, we select the lowest negative value. It is negative 25. Here it is. Then we find the ratios, so which is actually, but here we divide this by this. Well, and find that 300 is the minimum, the smallest ratio. So meaning that this row wins. And so this is the winning one. So this is actually how we can do the same using the tableau form. And later actually we will demonstrate the both formats of the solution. So in this one, we expressed everything, simplified. Remember that we didn't actually do this one because there is no x1 present, so that's why it stayed unchanged. we analyze the objective function if there is any potential to improve. And we see that there is, because there is one more positive coefficient, it is 15 at the variable x1, so therefore this is the pivot variable. And this column will refer to with x1s, will refer to the pivot column. Now we need to determine the winning actually row. The winning row will be here, this one. So that is row 3. Row 3 wins according to the ratios. Here we have 150 divided by 1. Then here actually we do not do anything. So then here we have 500 divided by 4, it is 125. And here we have 350 divided by 1. So it is 350, no, definitely 125 wins because it is the smallest ratio. And this is actually the summary of the step 1 basic feasible solutions. We see that x sub 2 has entered the basic variables, s sub 2 left it, so therefore that was the leading variable. Then x sub 1 is still 0 because it is here, and s sub 2 will be 0 because it is here. Okay? Because it is here, so it is 0, 0. Then as x sub 2 move to the basic variables, it is 300 now. S sub 1 is 150, S sub 3 is 500, S sub 150, and actually the z function value, the objective is 7,500. So as row 3 wins in the ratio test, so S sub 3 is the leading variable currently. So for step 2, so we extract x sub 1 through the other terms and substitute it into their objective function and all the corresponding remaining constraints. And here we have 9,375 minus 25 over 4 s sub 2 minus 15 over 4 s sub 3. For s sub 1 row, we have 25 minus 1/4 s sub 2 plus 1/4 s sub 3. And for S4, we have 225 minus 1/4 S sub 2 plus 1/4 S sub 3. Now let's see our final dictionary and final tableau. No, why final? Because if we look at the objective function, we see that all the coefficients are negative, meaning that there is no potential to increase the value of the objective function. Then about the solution, the right-hand side for the z is 9,375. Here it is. Just because s sub 2, s sub 3 were slack variables, so they are not influential. Then we refer to the original variables, and the original variables for us will be values for the original variables will be 125 for x sub 1 and 300, here's 1, here's 1, and 300 for x sub 1. So meaning that the basic feasible solution is optimal with the values of the number of product 1 units is 125, product 2 units is 300, and the maximum achievable profit for this function for the objective is $9,375. So thank you very much. That's it.